Hello everyone, my name is Cameron Hicks and my lab today is Lab 5, Slinky Simple Spring Motion. In this lab, we observed the motion of a falling slinky. The goal was to predict its motion and analyze how it interacts with its surroundings using video tracking and computational modeling. Our results showed that the bottom of the slinky remained suspended until the top collapsed onto it, which matched well with our simulations. Some basic physics principles and models. We have Newton's second law, F equals ma. The gravitational force, F of g equals m times g. The drag force, we use air resistance, F of d equals negative b times v. And then the slinky force, which is the tension in the stretch coils, which is just F of slinky equals negative ks change in L, which is distance, I guess. And then now we have the system and initial conditions. The observed system is the slinky, which is specifically the bottom end that was tracked. And then the surroundings were the Earth's gravity, the air, and everything else not part of the slinky, which is the camera, the room, or I guess the space outside, the experimenter. And the initial conditions was that the mass was 0.2 gram, or yeah, 0.2 grams. The height was 1.75 meters. The initial condition, the initial conditions for the position was negative 1.6 times 10 to the negative third, 2.7 times 10 to the negative fourth, and then 0, all in x, y, and z respectively. And then the initial velocity was 0 meters per second in each direction. And then some for the observational data using tracker, we recorded the slinky's motion as it fell. We noted that the top accelerates downward first, while the bottom remains stationary until connected by the collapsing top. Here's the video that reflects that. This was all used in tracker. So, and now I have the computational model. We use GlowScript to simulate the slinky's motion. The first phase modeled free fall with gravity only. The second phase included drag proportional to velocity squared. Initial positions and velocities from tracker were used, assuming negligible air currents. And then here is our first while loop, and this is our second. And they both reflect velocity and position update formulas. And now I have observations versus model. The model closely matched observational and observed motion. Both showed the bottom remaining suspended until the top reached it, but small deviations arose due to the unmodeled air resistance and minor variations in slinky tension. And as you can see here, the simulated curve is smoother. It's just this one predicted line. It's pretty uniform. And then, but the data that we found using the actual observed data is a little bit more sporadic, but they still resemble very similar results. And then some possible errors. That could be the tracking error, which is small mistakes in marking points in tracker, or a slight camera angle issues, which can make the observed motion look messy. We have the video quality. The low resolution lighting changes or camera shake may have affected the accuracy of position data, though this was out of my hands since I got this video online. And we have the model assumptions. The slinky's spring constant and tension behavior may not be perfectly uniform, causing differences from the model. Then you have air resistance, which is drag was only approximated in the model, so we could not really account for the actual variations in air resistance that could slightly shift the motion. And then some discussion and additional questions. Why does the bottom of the slinky remain suspended even though gravity is acting upon it? And this is because the tension holding it up doesn't disappear instantly. Gravity's effect can't reach the bottom until a compression wave travels down the slinky, which means that the top of the slinky has to meet the bottom first in order for that to move as one single object. And then how accurate is treating the slinky like a simple spring, and what advanced models could describe it better? And modeling it as a simple spring works for general motion, but a more accurate model would treat the slinky as a distributed mass with varying tension along its length. And then to conclude, the lab demonstrated that Newton's second law, gravity and spring forces can predict the motion of falling slinky. Our computational model successfully reproducibly observed behavior, highlighting the usefulness of combining video analysis and simulations to understand real-world physics. Thank you.